so I'm going to talk about some problems that my group has been working on for about 10 years, I would say, using ideas from geometry for problems in image processing, and more recently in the last 2 years, networks and machine learning. So these are very discrete, high-dimensional data problems. So I got interested in this. I think I might just tell a short story. So my background is, in fact, in nonlinear PDE and image in nonlinear PDE. I spent the first 10 years of my career working in fluid dynamics. And the story is a good example of how mathematics can really transcend across disciplines. So I've been very fortunate throughout my career to have some excellent funding from the US government. About 10 years ago, my program manager at the Office of Naval Research called me up and said, you know, we're getting into a lot of remote sensing applications, problems in image processing. And I know you work in fluids, and I know you work in surface tension and curvature, which involves higher order differential equations. I have a colleague, I have a principal investigator I'm funding, in fact, at Minnesota, Guillermo Sapiro, who has a problem in inpainting, filling in missing information involving a third order partial differential equation, a nonlinear equation. Maybe some of the work you do in fluids is relevant for this. And I said to her, you know, I'll tell you what, I'll fly to Minneapolis and talk to him. So I did. I spent 2 days in Minneapolis, and he showed me an equation. And he said, here's the equation. We don't know why it seems to work. In fact, we have to do some strange things to get it to work. But it produces these beautiful pictures. And after 2 days of staring at this equation, I kind of stood on my head and I said, I know that equation. That's the two-dimensional Euler equations for incompressible fluid flow, and you're trying to solve them with the Navier-Stokes boundary conditions. So completely different part of science making an impact in another area through the mathematical connection. And I think this is where we as mathematicians can really contribute in ways that scientists cannot, because we can see through the mathematics how to connect different fields. So you're going to see, I guess, some of those ideas in this talk. So that was my entree into problems in image processing. So today, where are we today with image processing? Today, a big term that comes up a lot is compressed sensing. So I'm going to talk about compressed sensing, and in particular, sparsity. So sparsity turns out to be very important in imaging because information is typically very low dimensional compared to the potential size of the data. When you go and take a picture with your camera on your phone, everyone has phones with cameras today. Typically, this has many, many, many pixels. You get a very high-resolution image, but somehow you can store exactly the information with all those pixels in a much smaller space somehow, you know, through things like JPEG, many data compression algorithms. The only reason why you can do that is because the actual content of the image is rather small. And so we're going to talk about that. Now, in terms of mathematics, what are some of the important, so you may see the word TV up here. So some people might look at TV and think that means television. No. Who knows what TV stands for? Total variation. Okay, well this is a country where there's a lot of appreciation for total variation. By the way, just to get a sense from the audience, how many of you are mathematicians here today? Okay, how many, are there physicists here? No? Okay, one. Oh, very good. My father's a physicist, so I have some appreciation for physics. You're a mathematician. Like, we'll think very broadly about math. Indeed. Okay. So we're going to talk about TV, total variation, and why it's critical for things like data compression. And that's really through ideas involving image segmentation. So now, where are we today? So there have been huge strides made in algorithms related to total variation minimization. So UCLA is a very active center for developing algorithms for total variation minimization, computational algorithms. When I arrived at UCLA in 2003, it would take us a couple of minutes to take, say, a 256 squared image and run a total variation-based denoising algorithm on that. Today, we can do that in a fraction of a second. And it's not the processor speed, it's the algorithm. So we're going to talk about that. These are some of the methods, the fast methods, due to a lot of very talented young people that have come through our group, and many of whom have worked with my colleague Stan Osher, who's taught me quite a lot about these ideas. Okay, so now I want to start with some very basic mathematics. So first of all, why total variation? So we're going to start with a very simple variational problem, and we're going to look at the heat equation. So we're going to look at the heat equation as a way to denoise images. I want to take some data, and that data is f. And let's assume that f is comprised of my desired image, which I don't know. So this is unknown. And of course, some noise. So I want to separate the noise from the true image. So one way I can do that is I can define a functional for this quantity u, and I can try to find a minimum for this functional. So here's a very simple example of a possible functional. This term here just says that I want to have u and f be near each other in an L2 sense. So that's a Lisa. So I'm going to use a lot of math terms very freely, since almost everyone here is a mathematician. So this is just a least squares fit to the data. And this term says that I want u to be somewhat smooth in some sense. Okay, so that's the H1 semi-norm. If I compute the first variation of this functional, I get a very nice linear equation. There it is. One way to, now of course you can solve this exactly by setting this equal to 0, but you can also, I want to think about the gradient descent problem. So if I take the gradient descent of this, so I just say set ut, L2 gradient descent. So I set ut to be minus the right-hand side, and what do I get? I get an equation for u which says it's going to satisfy a heat equation plus a forcing term, which demands that u approaches f pointwise. Now this works very well if my original signal is smooth. However, images typically aren't smooth. Why? Because you're looking at images, they're objects with edges. Edges have sharp boundaries, which means that if you think about it as a function, it's going to be L infinity, certainly in L2, but not typically not at all smooth. Okay? So that's a problem. So the heat equation smooths both noise and edges, so you're going to get a blurry solution to this. This is not the way to denoise an image. So here is a method that pretty much revolutionized image processing. This is the Rudin Osher Fatimi paper from Physica D in 1992. So this has been around for a couple decades now. And the main idea is to take the original functional and remove the 2. Okay, that's it. You get rid of the 2. And you might think, okay, that's very simple. You get the eraser, you erase the 2, and we're done. Well, no, because now we have the total variation semi-norm here, which is fine, except that if we try to minimize this functional, that gets interesting, right? The first variation, now that first term in the first variation of E is quite nonlinear. And this is why the algorithms 10 years ago were slow, because a lot of them were based on things like this gradient descent, PDE, okay? Which is, I mean, you can solve it. It's not impossible. You can write reasonably efficient code to minimize that thing. You can write semi-implicit code. There are a lot of things you can do, but it's certainly not fast, and it's certainly not something that you want to do in a real-time application. However, this is a very good problem to solve because the total variation does not penalize for edges. So if you have sharp edge information in your data, it will be preserved by total variation. Okay, so now what I want to do is just review some variational functionals from image segmentation. These are some famous ones. There are many papers in the literature, but I picked 3 that have been, I think, fairly highly influential. So this is the Mumford-Shaw. This is the Mumford-Shaw functional. So this is for segmentation. So we now imagine that we have some data. My data is now G. Sorry for the change of notation. My data is now G, and the desired solution is F. And I imagine that I'm looking for a solution that has that is smooth in most of the domain, but not where I have an edge. So gamma is the edge. I want to find this edge. Okay, so again, least squares fit to the data. I want the solution to be smooth away from an edge, but there's an additional term here, right? Now this is again where we see total variation coming into image processing, because this is a term that says I want the length of that edge, the perimeter, to be as small as possible. That's what we're measuring here. So we now combine all of these three things and we get the Mumford-Shaw functional. You can also do this very locally. You can just take a curve z parameterized by some local parameter s, and then you can write down a functional for the curve itself. This is what Dimitri Tertsopoulos and his collaborators did in their publication in 1987. They called this image snakes. This paper has had a huge influence on things like medical imaging. So this is a parameterized curve. There are now two terms that allow us to have a fairly short length curve, this one and this one. And then this term here basically is information regarding the actual data in the image. This functional here, so this is sort of a Lagrangian formulation. This is Eulerian. This is back to the Eulerian formulation. This is basically a simplification of Mumford-Shaw. This has also made a huge impact, the Chan-Vessey functional, due to two of my colleagues from UCLA. This came out in 2001. Chan and Vessey basically said, you know, Mumford-Shaw is a great idea, but it's a fairly complex problem because we're trying to have a smooth function away from the edges. We have to find the edge. You know, it's a little bit complicated. What happens if we treat an image as a very, very simple object? Suppose we treat it as something that's basically a constant in one region, another constant in the other region, and then some edge between the two constants. So this is basically taking what could be a very complex image and turning it into a completely a cartoon problem. Okay, so the only thing is we don't know the constants a priori, nor do we know the curve. We want to find them all. And so basically you need to find three things. And again, the length of the curve needs to be minimized here, along with the least squares fit to the two constants. But it turns out this is a very powerful technique, and it can be solved rather quickly. So now I'm going to make a connection between all of these problems and diffuse interface methods. So okay, so this is our total variation functional. One way we can interpret this is, it's kind of interesting because we bring back the H1 semi-norm again. So here's the H1 semi-norm appearing. So the 2 has come back, but it's come back with a double well potential. Okay, so some of you are familiar with this with the names Modica, Mortola. I'm using the name Ginsburg-Landau because in our group we're mainly looking at a specific choice of the double well potential, but we're basically talking about the same class of objects. So notice that there's a small parameter epsilon. So what does this do for us? The small parameter epsilon takes what would have been a sharp interface for the total variation problem and blurs it a little bit over some scales. And epsilon's actually, if we define it this way, epsilon is precisely a length scale. And it turns out there's a huge literature on the connection between these problems. And here what I'm doing is I'm making another simplification, which is I'm assuming my solution is somehow binary, meaning that it takes one of two values. So it's like the Chan-Vessey simplification. Okay? So most of my talk is now going to address this class of problems and what can we do with those. Okay. So one thing we can do is we can write down the gradient flow for the Ginsburg-Landau functional, and we get something called the Allen-Kahn equation. There it is. So this is an L2 gradient flow. This actually approximates motion by mean curvature, which is useful in image segmentation and actually in deblurring. Now, what you can also do, and it turns out there are reasons why you might want to do this. You can do an H-1 gradient flow. This gives you the Ginsburg-Landau. This gives you the CAHN-HILLIARD equation. So CAHN-HILLIARD is fourth order. I have two Laplace operators here. So it's a higher order equation, and it gives us a completely different dynamic in terms of the evolution equation for the interface. So this one actually approximates the Mullen-Sekerka problem, which is a non-local problem. There's a lot of rigorous literature about that. Also, this is conservative. So if we look at the total integral of u, it is conserved by this functional, by this right-hand side, whereas the Allen-Kahn equation is not. It turns out for image in-painting, we actually need to enforce more than one boundary condition, and this turns out to be a useful way to do that. So the Allen-Kahn equation, however, has an interesting history in image processing. I can't talk about everything, but I'm picking out a few papers that were certainly influential in my work. So one of our former postdocs at UCLA, Salim Esadoglu, who's now at the University of Michigan, noted that you could actually do quite well with blind deconvolution of barcodes. Barcodes are binary images, so they're white and black, very simple images. Deconvolution means that we have some data that's blurred. So you take a convolution of that data, and so that gives you an F, and you want to find the original U so that the convolution of U is close to F. So that's the least squares fit right there. And so how do we do that? We actually add a penalty term here, which demands that the solution somehow is small in our Ginzburg-Landau energy, which means that it's going to have almost sharp but not quite sharp interfaces, and otherwise is going to take on these binary values of the white and black. And so another reason why we want to look at these kinds of equations is notice that they give us back a high order term that's linear. Remember in my original two slides, I said this was a nice equation to solve. The heat equation can be solved very quickly. This one is not so good. What's beautiful about this connection from the standpoint of algorithm development is that the stiff term in the dynamics, right, this one here, has a first variation that's completely linear. It's just a Laplace operator. Very easy to solve numerically, and very fast algorithms can be used for that. Okay, so this is some background of earlier work. Now, a very important paper, which it has only made a little bit of an impact in image processing, but I think is going to have more of an impact in the high-dimensional data problem, is the threshold dynamics. Or colloquially at UCLA, we call it the MBO scheme due to the three authors, Merriman, Benson, Osher. But basically, the Allen-Kahn equation, if we take a small epsilon, to leading order gives us motion by mean curvature of the interface, okay? Now, there's another way to simulate that numerically without having to solve this PDE with a small parameter epsilon. And this is called the MBO scheme. If you don't know it, you should, and it's incredibly trivial to compute. So what you do is you start with an interface, you take the characteristic function, which is the inside of the stuff inside the interface. You run the heat equation with that as the initial data. So you just blur slightly this characteristic function, and then you threshold. And then you repeat that process. Blur, threshold, blur, threshold. And if you do that, the interface actually follows to leading order motion by mean curvature. So that's the MBO scheme, and it turns out we can use that, and we will use that. I'll show you some examples. But the paper that was sort of influential to me is by Esadoglu and Tsai from the Journal of Computational Physics in 2006, where they basically showed how to do Chan-Vessey segmentation using MBO. And when it works beautifully. In like 4 iterations, you get the solution of the Chan-Vessey segmentation problem. But it doesn't always work, so that's a tricky thing. All right. Inpainting. So here's a cartoon picture of inpainting. So what we have is we have an image where we have some region that's unknown. We want to fill in missing information in this region. Okay, so we've just put random pixels here. Now, if you're an artist, you're going to look at this and you're going to try to continue the black through, just like it is here. You're going to try to continue the black portion of the circle here while you not only continue the black continuously across the unknown region, but you also want to continue the direction of the edge as well. And so you can see if I use I could use total variation as a metric for trying to complete what's going on here. And if I do that, notice that I do fill in very nicely the black, but the direction of the edges is not continuous. I have a jump discontinuity in the edge, the direction of the edge. So it turns out that if instead of running, so you could do the Allen-Kahn equation with this. You could use a diffuse interface method. If I actually use the CAHN-HILLIARD equation rather than the Allen-Kahn equation, I get, this is not what's actually, this is a different paper here. They did something else, but we discovered that in contrast to what was done in this paper in SciApp in 2002, we could actually run in fact, here it is, the CAHN-HILLIARD equation. So this was a bit of a hack, but you know, when you're designing algorithms, at the end of the day, you want it to work, rather than necessarily have beautiful mathematics. So this was kind of on a lark. Selim was visiting me at Duke at the time, and we were going to try to use diffuse interfaces to solve a rather complex higher order minimization problem to do inpainting. And then we thought, well, let's just, to test our code, to bench our code, let's just start with the CAHN-HILLIARD equation, just to try it. So we said, well, if we're going to run CAHN-HILLIARD, we need to add a forcing term, which basically demands that in the known region, okay, that the solution looks like the data, okay? So notice when I add this forcing term, I end up with a weird PDE. This is an H-1 gradient flow. That's my CAHN-HILLIARD equation. This is an L2 fidelity term. So they don't necessarily go together, but you kind of have to do it this way in practice. So we just ran it on the computer, and it worked beautifully. And we thought, oh, look at that, you know? So yeah, so here are some examples. By the way, my sponsors wanted me to try Arabic, just so you know. This was not my idea, but you know, when the Department of Defense is funding you, they say, oh yeah, Arabic, would you please run that? So I did. And it pays for more students, okay? So that's how you get more students out of the government, is you run what they want you to do. This was a fun example. This is UCLA logo. And the Trojans, by the way, is the name of the mascot of our rival school in Los Angeles, USC. You guys wouldn't know that necessarily. That's okay, but just so you know. So this would be what happens if the students from USC on the day of the big football game come and deface the campus. They would do this, and so then we have to remove their writing. And we do that using, of course, image inpainting. What else would you use, right? So at least digitally. Okay, so this is my brief story on image inpainting, and this was a fun project. Not only, so we basically stopped. When we got this to work and it worked so well, we decided, why should we solve a more complicated problem, because this actually works. And then we went on to develop some theory. So although this was a bit of a hack, you actually can look at this. So this is not a gradient flow. We're not minimizing an energy, but nevertheless we can try to prove something about it. So we were able to prove, for example, that we get the right boundary conditions. So for example, when we fill in these missing lines, we get not only continuation of the colors, but also of the direction of the edges, which is what we want. And that's because of the fact that it's because of the fourth order operator here. Okay, so we had a bunch of papers, and we even got a US patent out of this because it was a fast method. Okay, so why is it fast? Well, it's fast because we can exploit some basic ideas from computational PDE. How many people here numerical analysis, computing, any computational people? A few. All right. So, okay. How many of you analysis of PDEs? A bunch. All right. So this is a lesson for those of you in analysis of PDEs, because you're going to understand this, that there's a lot of problems out there in numerical analysis you might want to work on, you know, because all right. All right. So here's the basic idea. So so notice that these energy functionals I'm working with, where are they? They went away. This one. Very non-convex because of this. This is obviously convex. This is highly non-convex. Double well potential, very non-convex. So I'm stuck with a non-convex functional I'm trying to minimize. But we can exploit that to design what we call a convex splitting scheme. So it's a very simple idea. So I take my energy functional, I write it as a difference between a convex and a concave part. I guess these are both convex if it's a difference, right? So you write it as the sum of a convex and a concave part. This is not a unique decomposition, obviously, because I can add a convex functional here and subtract it here, right? So it's not at all unique. So it's a bit of an art how you choose these two. So the first thing is you choose them in the right way, whatever that is. And then our time-stepping scheme for the gradient descent now has, so it has two pieces here. Notice that this is evaluated at the new time level. Okay, this is the implicit part of the scheme. This is the old time level, and this is my new time level. So this is just an approximation of the time derivative, right? And I've multiplied by delta t here. Okay, that's the old, and this is the old time level. So now here's the art. So you have to do this in a way, so now what I'm going to have to do numerically, this is the hard part, numerically, is I'm going to have to solve this implicit equation for the new time level, okay? So notice that if I happen to put here the H1 semi-norm, I get the Laplace operator right there, okay? That's good because I can now take the solution at the new time level and I can project onto the eigenfunctions of the Laplace operator. And if it's just a differential equation, there's a good way to do that projection. It's called the fast Fourier transform. And the fast is no joke. It really is fast. Okay? So that's what we do. So then you basically, on every time step, you project with the fast Fourier transform onto the Fourier modes, and suddenly this problem diagonalizes in the Fourier domain. Boom, done. Okay, so it turns out that you can do this in a way typically so that you end up with a scheme that's unconditionally stable, and it allows you to do some great stuff. So, so for example, Peter had to go because of his daughter, but Carola was a student of his, Carola Schonlieb. She's now at Cambridge. She's a professor in Cambridge. But we have a paper where we actually do some of the numerical analysis for various higher order equations from INPAINTING in case the analyst you're thinking about, maybe you should think about working in some numerical analysis. Nice set of problems. Okay, and in case you want to see how it works, so here's the CAHN-HILLIARD case. Notice that I like this example because this is an example where you might not actually want to use CAHN-HILLIARD. Notice that this is the unknown region, and this is what we get for a completion. And you see it does a beautiful job of continuing smoothly the direction of the edges. Right, the direction of those. So that might not be actually what you want, but if it is what you want, then you get this. Okay, and we can use it for all sorts of cute. Now these are binary examples, but we can also use it on grayscale. You might wonder, how do we do grayscale? Well, what we do is we say, okay, remember, images are digital. So we don't actually have a continuous function for the gray values. We actually, even the gray levels are completely digitized. And so, we might have an 8-bit or a 16-bit, depending on the resolution of the image, gray level. So if it's 8-bit, that's basically a binary representation of the grayscale, which means I can take each of the decimal places in my binary representation of the grayscale value, and each of those is a binary problem, black or white, 0 or 1. So what I can do is now take an 8-processor machine, and on each of those processors I can run a binary black and white INPAINTING problem for each of those bits. And then I can combine them together. So it parallelizes very nicely, and we can easily do grayscale INPAINTING using that idea. So we were all excited about this, and then I had a student, Julia Dobrozatskaya, who was trained in Russia originally. She has a beautiful Russian name. And she came to me at UCLA at the beginning of her PhD and said, I know wavelets. I love wavelets. I want to work on wavelets and image processing. What can you give me to do? And I said, I don't do wavelets. I know something about them. They're nice. They're a very, very nice representation of L2, nice basis for L2, lots of things you can do with them. And then we started thinking about what could we do with wavelets, and we realized that there were a lot of beautiful problems in them. So first of all, let me back up a little bit. So one reason why we like to use wavelets is because they are a nice basis for L2, but they're a basis where the basis functions are localized. And that's why they're quite good for image processing, because images typically are composed of fairly localized pieces of information. You really don't want to use the Fourier basis to represent an image for many reasons. I mean, we can also talk about things, well, for many reasons Fourier is not so good. So what we decided to do was reinvent the Ginzburg-Landau functional without the differential operators. We decided we were going to use operators based on wavelets. So how do we do that? Well, you can think of the key differential operator in the Ginzburg-Landau functional is really the Laplacian, because that's what you get from the first variation. And we can write the Laplace operator. You can easily write it by just looking at how it acts on each of its eigenfunctions, right? So I can just project onto the eigenfunctions. So suppose I construct an operator now that has eigenfunctions. I'm going to define the eigenfunctions as some wavelet basis functions, and I'm going to have the eigenvalues scale just like the scaling of the Laplace operator. Right? I can do that because if we think about so for those of you who don't know what wavelets are, I'll just say it's an interesting choice of a basis for L2 that has a dyadic scaling, so a factor of 2 scaling in space. So the J component, so K gives me the translation motion of the wavelet. The J component is the scale, and it's dyadic, okay? So there we go. So that means that I need to make this the choice, the corresponding choice of the eigenvalue associated with my operator. So I'm gonna cook up an operator to look like the Laplacian, but with eigenfunctions that are wavelets rather than Fourier, okay? So you can do this, and then you can basically rewrite your Ginzburg-Landau functional. And we did this, and we published it in IEEE, and look at it. So for example, if you want to do barcode deblurring, why should you use Fourier? You really want to choose a basis function like the Haar basis. Because the Haar basis they're exactly the right basis function for a basic 2-dimensional barcode, and you can get beautiful results this way. You can also use it for things like grayscale in painting. And then once you do this and you discover that it works pretty well, you can do some analysis. So we have a paper that came out, I think, 2 years ago where we looked at the gamma convergence of this redesign. So here it is. So we have now, here it is. No, this is Ginzburg-Landau. This is the wavelet Ginzburg-Landau. So all we do is replace this functional here with, and it turns out to be a Bessoff semi-norm. So for people who know Bessoff spaces, that's what it is. So it actually has a very nice format here. And then you can actually prove a theorem about gamma convergence. Really, Julia did this. She deserves the credit for that. Julia just got a tenure-track job, by the way, at Case Western, so I'm very happy for her. She's moving out. She's a postdoc right now at University of Maryland, going to Case Western. So, okay, so this is complicated. I'm going to explain that with pictures. So you end up with a gamma convergence to a functional which gives you a Wolf shape energy. So it's very close to total variation, except that there's a bias in the direction of the edges, okay, which we can quantify exactly based on the choice of the wavelets that we use in the definition of that Bessoff semi-norm and how we weight them, which is kind of cool because what you end up with are, so these are minimizers of that functional. These are constrained minimizers. So we just thought for fun, we'd solve the constrained minimization problem where we minimize this functional subject to a fixed volume constraint. Okay, so we demand that the solution has some total integral, and you're stuck with that. So that gives you a non-trivial solution. If we had total variation, the answer would be a circle with a prescribed area. Okay? Because that's the solution of the curve shortening problem, where when you have bias in the direction of the edges, you end up with minimizers that are Wolf shapes. Okay, so that's spelled W-U-L-F-F. In case you don't know, it's not the animal wolf. It's spelled differently. I didn't write it here. But anyway, so you get these, they're sort of crystalline-like in their structure, and they inherit the symmetry of the wavelet basis. The wavelets are, so this is a problem with wavelets. Unlike Fourier. Fourier basis is rotationally invariant. The wavelet basis is not. It feels the Cartesian coordinate system, and that feeling is inherited. That symmetry issue is inherited by the minimizers of the functional. Interesting. All right, so since I don't have forever to talk, and you guys are really great in listening to everything, I'm going to tell you now what we're doing now with these ideas, and we're going a little bit crazy with the diffuse interfaces because we're now applying them to problems on graphs, so high-dimensional data problems. Okay, so PDEs on graphs. So our first paper on this came out just this past year, a few months ago actually, in multi-scale modeling and simulation. It was joint work with my colleague Arjuna Flenner. He works for the Navy. He's a mathematician. You may be wondering, what is this? Okay, we're just now starting to apply our algorithms to a data set that is related to this. This is actually a rivalry network of street gangs in the Hollenbeck division of Los Angeles. Okay, this is a small geographic area where we have about 30 street gangs that fight with each other. Okay, so yeah. So for example, this gang here is rivals with all the ones that it's connected to, but not these over here. Okay, so the assumption is that none of the gangs are friends. Okay, that they only fight. They only fight. Exactly. But before I get to this, I need to explain the mathematics. I put this up to wake people up because this is the point in the talk when everyone starts to sleep because it's too many epsilons and Laplace operators, right? And so, but then they're like street gangs. Oh, I gotta wake up and listen to that. Okay. All right. So now I want to describe how we're going to define our graphs. So in a typical application, we have a huge data set, but each piece of data is sort of structured the same as every other piece of data. So one example might be, you look at the Congress and you look at how they vote, and so everybody has the same list of votes, just they have different votes, right? So we're going to look at that example. So X and Y would represent what we call feature vectors, just some big vector of data associated with two different data points. And then this would be how we would define the weight associated with those two nodes. So each piece of data is a node on the graph, and then you have a weight that connects those nodes. So that's how we start. These are weighted graphs, okay? Okay, so examples would include the voting records of Congress, and back to image processing, non-local means image processing, beautiful idea, where every pixel has a neighborhood of pixels. So I look at an image, I take a pixel here, I take a pixel here, I take a patch around this pixel, I take a patch around this pixel. That gives me two feature vectors. Rather high, they can be very high dimensional depending on how large a patch, and then I can compare those. If I do that, I get a very complex graph because I have weights now that connect every single pixel to every other pixel. Computationally very expensive, but I'm going to show you it does some really interesting things. So there's a history to these non-local means graphs and imaging. So I'm not describing everything here, but I'll mention some key papers. So Boati's, Collin, Morell in 2006 introduced this for imaging applications. And then in 2007 and 2008, Osher and Gilboa developed a non-local TV calculus for these graphs. And that turns out to be very effective for in-painting applications. I'll show you some examples. Like I described in image processing, you now have a huge high-dimensional graph problem where every node on the graph is connected to every other node. So that's a very computationally complex problem. And one of the issues with the Osher-Gilboa method is that even with really fast total variation minimization procedures, it's typically slow. So what we've been doing in my group in the last 2 years is generalizing these ideas to more machine learning problems and bringing in diffuse interfaces. So bringing in the Ginsburg-Landau functional and the MBO scheme, and with some great results. I'm going to be immodest and say I think these are really nice results. Okay, so here's the basic idea. We have a weighted graph. I can define the graph Laplacian for my weighted graph. I can then define an inner product with the graph Laplacian and the data U. And so this is basically my discrete H1 semi-norm. Okay? I can normalize the graph Laplacian. That needs to be done sometimes. I won't go into details other than to tell you it needs to be done. So this is a symmetric normalization of the graph Laplacian that involves the degree of the nodes in the graph. Once I have a good definition of the graph Laplacian, I can define a Ginsburg-Landau functional with a penalty term here, with a penalty term involving data. So look at this. This would be my new version of the Ginsburg-Landau functional. This is the double well potential again. This is the H1 semi-norm for the graph. I have a small parameter epsilon, and I have a least squares fit to the known data. So this lambda is a parameter that has a magnitude, but it also tells me if I happen to know the data is this at this particular value, that I'm not going to do a hard enforcement of that. I'm going to do a soft enforcement by using a least squares fit. Now I have an energy functional I can try to minimize. Okay, this is a slide that shows you why you sometimes want to normalize graph Laplacian. It also shows you why the non-local means graph is a very interesting object, especially in image processing, because look at this. If I have the proper normalization of the graph Laplacian, the top eigenvectors for the graph Laplacian are picking up all the major features in my image. Okay? If I use the Fourier basis, I'm not going to see the cows. No, I'm going to see sines and cosines, right? If I use the wavelet basis, I'm going to see wavelets. I'm not going to see the cows. Okay? But here what I'm doing is I'm defining a Laplace operator that has the data built into it in some way, which is pretty cool. Okay? And so we see the cows. And by the way, the graph theory community has been getting a huge amount of mileage just out of linear methods. Okay? Spectral clustering, for example, which is huge. Okay? Spectral clustering is a linear problem. Because why? Why does it work so well? Well, you can see it. Because the information is built into the spectrum. Okay, so some math, a little bit of math. So we've been doing some work, some theory now. It turns out, okay, I don't have a lot of time. So I'm just going to say you can actually prove things like gamma convergence for this, well, okay, this is a variant. This is a variant of the Graf-Ginzburg-Landau functional. But anyway, you can take a variant of it and you can get a convergence result to, not surprisingly, a graph total variation functional with the same weights. So total variation comes back, which is good. This is a recent paper with Yves van Gennep as a postdoc with us at UCLA. So now I want to show you what you can do for high-dimensional data clustering. So here's a classical test problem in machine learning. These are the two moons, okay? So what you have are, so you might think that's kind of stupid, right? I mean, I can look at that and I mean, a child could segment, right, by hand. Okay, now I'm going to tell you what you're actually looking at is data that's embedded in 100 dimensions, projected onto 2D so we can visualize it. So the computer is trying to take data in 100 dimensions and it's trying to pull it apart. And the reason why it's hard is because the computer can't see that with the computer's eyes. The computer doesn't even have eyes, right? So we want to automate this. And so you can see the second eigenvector just doesn't give, in fact, if you look at the spectrum, you don't get a segmentation. This is an example designed to break the spectral clustering algorithms, and it does break them. But if we run the Ginzburg-Landau method, look at that. It does really well. And when we originally started working on this, we thought this was a bit of a novelty, and so we started benching our code. We used convex splitting. And we started benching our code against the, sort of state-of-the-art from the year before. So this was Hein-Buehler 1 Laplacian algorithm. We actually got more correct and were faster than them. We thought, okay, maybe this is more than just a novelty. So here's another example. I'm in the United States. I live there. So of course we look at data from the United States. But I'm sure you can relate to the local politics here. So this is, okay, so we don't use 2013 data from the US Congress because it's very polarized. We use 1984 data, which is harder to segment because they didn't all vote so much along party lines. So this, I like this example because it shows that we can sort of spy on people in some sense, right? We can say, suppose you don't know which party the Congress is in. So you don't know, you just have the Congress and you're just looking at how they vote, and the knowledge of which party they belong to is hidden from you. Okay, so somehow that's hidden. Okay, but maybe it's not completely hidden, and this is what we mean by semi-supervised learning. In semi-supervised learning, we go and find out the party affiliation of about 1% of the Congress, okay? So that's not hidden, the rest are hidden. And then we try to figure out who's in which party based on how they vote. So this is a binary segmentation problem. So it's a beautiful application for this. And we can, in this one example, we can get about 96% correct classification with 16 votes from the 1984 Congress. You might say, is that good? Well, it's pretty good. Okay, so here you might wonder, why are we showing you pictures? This is a joke, but you may wonder, why am I showing you so many pictures of the same cows? Well, my collaborator who did the computing works for the US Navy, and he has to get somebody in an office to approve every paper that he wants to submit for publication, not to contain sensitive information. Okay? So instead of putting pictures of airplanes in the paper, we put pictures of cows because we figured they would just take one look at this and stamp it and send it out. So that's why. So that's why we have cows, because they're really not sensitive at all. Okay, so now I want to explain why. This type of method allows us to. So why we can do this calculation very fast. So this is another semi-supervised learning where in this image you have a person go in and hand segment the cows rather badly, actually. So somebody goes in and just, an analyst comes in and says, that's my object of interest here. These are the suspicious cows. Can we find those cows automatically in another image? So you know what? You can see the black one here, but not on the screen. So on my computer, you can see it. It really, okay, that one, this one is clearly showing up, but this one does too. It's just that the projection is not very good. Okay, so this is an example of a problem that's very computationally expensive because I'm now connecting I'm doing non-local means, so I'm connecting every single node to every other node. I want to do that because the non-local means will pick up the texture here, okay? And so it turns out that there's a trick you can use, and this is why I think these diffuse interface methods are so nice for these problems. Because remember, if I go back to our convex splitting algorithm, let's go back here. Whoa, where is it? There it is. Okay. So go back to convex splitting. So remember that I'm just going to tell you that in a typical application, this is often the sort of higher order differential operator. So this would be our graph Laplacian sitting in this term here. And so one way to solve this implicitly is to project this onto the eigenfunctions of whatever this operator is, okay? And so it turns out that when you're working with, here we go. Yeah. It turns out that when you're working with these non-local means graphs, you have a fairly small number of important eigenfunctions, okay? I mean, much, much smaller than the total dimension of the problem. I mean, we're talking like, you could have, in a typical example, we might have 10,000 nodes on the graph, and we only use 100 or 200 eigenfunctions. So that means that the expensive part of the calculation, I only have to compute something, so it's sublinear is what I'm saying. We end up with a calculation that's basically sublinear because we don't have to compute for every eigenfunction. If you were to solve a differential operator, if you were going to use the regular Laplacian with the Fourier transform, you cannot cut out the high part of the spectrum. You know what happens if you do that, right? You get Gibbs phenomenon, you get all sorts of horrible things. Why? Because there's information contained in the small scales that's really important, especially in image processing. However, if I use the non-local means graph, it turns out that most of the eigenfunctions are just noise. They really have no important content. So that's another beautiful thing associated with this particular spectral method. Okay, so I have more slides than I'm going to have time for. So I'll just tell you that we can use the same idea for in-painting, and we can speed it up by about a factor of 5 using the MBO scheme, the thresholding heat equation scheme. So what you can do is you can propagate a graph version of the heat equation, and then you can threshold. And this is very simple, and it basically can converge sometimes in just a few iterations. So for example, there's a machine learning data set called MNIST. It's handwriting digit recognition, like your post office would use to read envelopes, handwritten letters. And we only need 4 iterations of this for the MNIST data set to get convergence. So this is the algorithm. You create a graph from the data, you choose the weights, you get the symmetric graph Laplacian, you calculate the eigenvectors and eigenvalues, and this is the key part. It's only necessary you only even have to calculate a portion of these, and there are fast methods for doing that, like the Nystrom extension, which comes from the graph theory community. And then you just iterate this simple 2-step scheme. So it will do things like the 2 moons, it will do the cows, and it turns out, so this is where we got really excited because we went back and said, we asked my colleague Stan Osher, we said, what's the state-of-the-art fastest method in non-local means total variation minimization? He said split Bregman. So we got that code, and we benched it against our code. Whoops, that's the wrong slide. Here it is. We benched it against, so this is our code, and this is the previous state-of-the-art. And you can see the runtimes are about a factor of 5 or so faster using the diffuse interface idea and using the MBO scheme. And so this is why, so you may wonder, why would I want to use these crazy non-local graphs? So here's an example with texture. If I use local in-painting on the texture, I don't get the stripes back. But if I use the non-local method, I really get that texture back in great detail. So that's an example. Okay, so how much time do I have?
4 minutes.
4 minutes, perfect. Okay, so once you see that there's a beautiful connection between total variation, the Ginzburg-Landau functional, and doing all of these things on graphs, you can start asking yourself, what about other graph problems? So there are famous problems in graph theory, like graph cut problems, that can be written exactly in terms of total variation minimization. So the Cheeger cut, the relaxed continuous Cheeger cut problem, this is work done by some colleagues of mine, former and current postdocs from UCLA, can write the Cheeger cut problem as a total variation minimization problem on graphs. And they actually solved this one using a split Bregman algorithm. This just came out in this fancy NIPS, computer science NIPS conference this past year. Okay, and you might think, okay, is the whole world always binary segmentation? What happens if you want to do segmentation with more than just 2 classes? Very reasonable question to ask. Here is a beautiful example with 10 classes. We have the numerical digits from 0 to 9. And we have handwritten digits, and we want to automatically identify which digit we're looking at. Now, a human can do that, but that actually maybe you want to do this much faster than a human. Okay, so it turns out you can easily generalize the Ginzburg-Landau functional to multiclass. This is not a new idea. So we're borrowing from ideas in material science. So instead of having so what we do is we say, okay, now, instead of having a scalar value u that's either going to be 0 or 1 or -1 and 1, what you do is you embed it so if it's n classes, I embed it in n-dimensional space, so it's a vector. I now have vector valued minimization problem where I use the simple, I write down a multi-well potential on the simplex in n-dimensional space, where the wells live at the nodes of the simplex. So it's completely symmetric. That's the thing, is you don't want to bias any one of the classes. So it has to be symmetric with respect to all of these different classes, semi-supervised learning, and the graph Laplacian. So I can do this, and everything extends quite nicely. And we can now do multi-class segmentation. So here's 3 class. By the way, this paper, I should give credit. This paper was written by several of us, including 2 very talented PhD students, Christina Garcia and Katie Merkuriev, and my colleagues Arjuna Flenner and Alon Perkis. And we just submitted this like 2 weeks ago. So here's 3 class, here's 3 moons. And what we're doing here, semi-supervised, we're using 5% of the ground truth, and the rest is unknown. This is just grayscale, multicolor segmentation. It can do that basically perfectly. But now if you want to look at machine learning applications, you really want to use these. There are sort of standard benchmark tests. So one of them is this MNIST data set. And here we are. We're doing quite well on MNIST. This is with 3.6% of the digits known. And I think we're running this on about 40,000 digits. So we take a data set of 40,000 digits. We assume 4% of them are known. The rest are completely unknown. And this is how well we can classify them in a very, very short amount of time on a desktop machine. All right. So this is, in case you're wondering what's the speed issue here, the graph calculation is actually the most expensive part, and then the eigenvectors are the second most expensive part. And then the actual running of the minimization problem is pretty cheap. These are just some other machine learning, sort of typical machine learning benchmark tests. And here we are. We're doing quite well compared to other methods out there. We're basically beating or equivalent to other methods. So I'm pretty excited about this. So now I'm going to end with the gangs. I'm going to mention the gangs again. Now I'm going to need to wake you guys up again, so I'm going to mention the word gang. Okay, so So I have some good colleagues who work in social network analysis. This is not my area of expertise, but I'm learning about it. So I have one colleague, Mason Porter at Oxford, who he's also, by the way, he's also an American who's living in the UK right now, from Los Angeles originally. So Mason is an expert on graphs and I mean on social networks. With social networks, you typically don't know how many groups you have in the network. You're trying to find that out. So we can't say, oh, we have 5 groups, let's find the 5 groups. We have to figure out the number of groups as well as figuring out what the groups are. And so that introduces a concept called modularity optimization, which is a rather complicated functional, which I don't have time to go into lots of detail. But I'll just say that it's very combinatorially complex because you have to figure out the number of groups as well as what the groups are. And so this is fairly, I mean, this is like within the last 10 years this was introduced. There's a lot of work in the physics literature on this, not as much in mathematics, but these are beautiful variational problems for people who like variational problems. So we should do some mathematics on these because these social networks are really interesting problems. So since I don't have much time, I'll just cut to the chase. This is an idiom, American idiom. Cut to the chase and just say that it turns out that the modularity, it turns out you can write the modularity optimization problem as a total variation minimization. Okay, so everything is total. So at the end of the day, the moral of this talk, the take-home message is the total variation is everywhere. Okay, it's everywhere. So here it is again. So right, so this is a simple example where we just say, suppose you only have 2 groups. So suppose it really is binary. Well, it turns out you can rewrite modularity optimization as a TV minimization with, an additional penalty term. But if you assume you have n groups, not 2, but the case of the multi-well, okay, so you have a fixed number of groups. Again, you can rewrite it as total variation minimization. So we see now that we should be able to solve modularity optimization by first saying, suppose we have 2 groups. Then we're going to solve that using TV. Let's suppose we have 3 groups. Then we solve that one. And we just solve for some, lots of different n's. And it works. And so you can actually, so for example, if we take the 2-moon data set where we assume we know nothing, so we have it's not semi-supervised, it's unsupervised. Okay, so we want to know not only what the segmentation is, but how many groups there are. Modularity optimization will tell us there are 2 groups. And there they are, and it does it perfectly. And this is using our algorithm applied to this problem. So here's a case of 3 point clouds. We can see, of course, where they are. Now this modularity will tell us there are 3, and there it is, and there they are. And so you can start applying this to some pretty complex social network data, which I don't have a lot of time to go into, but I'll just say this is work of my PhD student Hui Hu. That hopefully will be posted on my webpage and submitted within the next week or 2, I hope. I need to write to her telling her that I'm going to be on YouTube telling everyone that her paper is about to go online, so that she needs to do this. She's very good, so I'm sure it'll be great. So here's where we're excited about this method. So for example, if we take, this is just a simple example, where we take, again, the MNIST data set, the handwritten digits. We take 2 specific digits that are really hard to segment, the 4 and the 9, because when they're handwritten, they look a lot like each other, the 9 and the 4. So that's one of the challenging ones, is you just take those digits and you try to segment them. And we can apply a classical, pretty much state-of-the-art community detection algorithm called Gen-Louvain. And it will tell us that there are 2 classes within this data set. It tells us that. And it takes 110 seconds to run on this many digits. And our algorithm pretty much gets almost exactly the same numbers, but it takes about 1/10 the amount of time to run for that size data set. So we're pretty excited about this. And I guess at the end of the day, the moral of the story is that there's a really beautiful mathematical connection between these graph problems, total variation minimization, and diffuse interface methods. I think we're just starting to get into this, and I think there are a lot of good problems out there for mathematicians. So since I'm really at the end of my time, I think I said all of this, so I'm just going to stop there. And oh yeah, and I have an advertisement. So if you are into this stuff and you like this stuff, we are going to be running a cluster group. This is like a small group of researchers working together on this at ICERM. ICERM is the Institute for Computational and Experimental Research in Mathematics at Brown University. It's an institute funded by the U.S. National Science Foundation. I'm on their science board. And so I'm putting together this cluster group that will run in February of 2014, exactly 1 year from now. If this sounds interesting to you, let me know, because we have funding for people to come. It'll be about a month. And there's also going to be a workshop, and we're looking for some more core participants. So I think I'll stop there. Thank you.